Good afternoon, everyone. This session probably will be slightly bigger, but the coffee break it seems to be more attractive at the moment. This session will speak about some optical technologies, especially focusing on Flexgrid and the related technologies. And our first presenter will be Mr. Marc Lyonnais, who is responsible for advanced research network architecture programs in CNS-CTO group. Prior to this one, he was responsible for research and development of system architecture and inter-system verification technologies. Marc previously worked for Nortel Networks. Over the past few years, he was responsible for several NREN projects, including the Advanced North Atlantic 100G submarine research network. Currently, he will speak about 401 terabit transmission system in real-life environment. Marc, the floor is yours.
Thank you. Good afternoon, and thank you for attending this session. So indeed, I'm going to talk about 400 gig that was demonstrated at SC13. And basically, what I would like to go through today is start with an introduction and why I want to talk about SC13 and 400 gig. I'm going to describe a little bit the technology that was involved, that is involved as well in 400 gig, which include Flexgrid. And basically, I'm going to talk about the 400 gig itself experiment that was done at supercomputing. So first of all, Ciena has always been a firm believer in Cynet's pivotal role in leading-edge technology. So Cynet is a group made by the top network engineers from all the NRENs around the world. And basically, they always like to push the vendors in terms of technology requirement to make the best network there is. And basically, when we kept with this tradition, Ciena offered to the WAN team of C13 if they would like to benefit the 400 gig technology. ESNet and Internet 2 has also offered to basically fill that pipe, that 400 gig pipe. And basically, this is what we're going to talk about. And how it was possible to do, and we will describe the technology and its benefit related to this activity. So let's talk about the technology. As far as Ciena sees it, there's three dimensions to evolve the capacity evolution. First, you can always increase the symbol rate. That got us going for the last 30 years. Then you can improve the spectral efficiency, or basically jam together a lot of wavelengths together to have a bigger super channel, if you will. And another way that was really disruptive in the technology was to move away from an amplitude modulation where we're sending only ones and zeros to the fiber optic by flashing the laser to basically send symbols and in introducing what the wireless technology guys are really used to, the coherent technology. So the basic requirement of a coherent modem is basically using a lot of software or digital signal processing to change the type of modulation. If you remember, some of us should remember the screeching on the modems back then when we were looking for the best baud rate possible on that telephone line back then. The screeching was basically different type of modulation map that was received by the other end of the receiver. And basically, they was basically asking if they could hear the transmitter talking better than before and basically choosing the higher bit rate. And basically, that would allow the modem to choose the right dispersion map and the right symbol map. The second one is to have some embedded intelligence. What we mean by embedded intelligence is basically the capability of choosing the right set of parameter to have that communication channel be operatable. It also allows some capability that are relative to a coherent transmission system. So since your receiver and your transmitter are coherent, there are some assumptions that are taken into account at the receiver level. So you're supposed to know what you're receiving. Therefore, there are some parameters that you can compare. And like this, you can have some test set capabilities into that. And then there's forward error correction. There's two types of forward error correction. There's a hard forward error corrector, and there's a soft forward error correction. And I will describe that a little bit more onto another chart. And that basically, the history has told us, and has taught us as well, that hard FEC was a very good way to start enabling the 10 gig transmission having a better reach. And then there was other techniques that were used in the wireless technology where we could actually use probability to increase this decision threshold on some, and use the probability to basically perfect the receiving error rate. And then there's spectral shaping. There is no point thinking about sticking a lot of channels next to each other if they're going to interfere among one another. So the theoretical approach is a brick wall type of shaping. If your carrier is shaped like a brick wall, you can put a lot of them next to each other without interfering. So spectral shaping is extremely important when we're talking about super channel and flexible grid. And again, I will expand a little bit onto this. Let's start with the importance of pulse shaping. On the top, if you remember your engineering communication mathematics, if you had a beautiful eye diagram here, well, that translated itself on a carrier with a lot of side modes. If you're adding a lot if you want to remove those side modes, you basically have to add some other signals into it that will cancel out those side modes. And basically, your transmission signal will move from a very broad signal that, if you could see, was fitting right here in the 50 gigahertz grid to a more narrower. That gives you a lot of good thing to work with when you're thinking about super channel and when you're thinking about flexible grid. Then there's forward error correction. Typical signal with no forward error correction cannot survive with a lot of noise. So the bit error rate tends to go really down with a little bit of noise. If you add forward error correction, well, you're able to survive with a lot more noise, and you can actually improve the system reach. The soft FEC decode, what it basically gives you, it moves you away from what they call hard decoding, which basically you receive a bit. And I will basically expand onto this. I have a little clip which you're going to be able to basically appreciate a little bit more live. What I mean is, once you receive a 1 and 0, if you take a hard FEC, you're basically using a polynomial. You're putting it through the mathematics, and you're basically choosing a 1 or a 0. Whereas if you take soft FEC, you're using the probabilities and basically learning from the incoming signals what the signal was supposed to look like, and basically you're improving your reach and your decision threshold by a factor of 2. So what does 100 gig look like? Well, everybody talks about QPSK and 50 gigahertz. QPSK means quad phase shift keying. So therefore, there's 4 symbols. Each of these symbols have, like, think of it about a coordinate Cartesian axis, if you will. Each of these coordinates have basically correspond to 1 symbol, and they have 2 bits. So when the receiver decodes that symbol, it actually understands 2 bits. That allows us to decrease the line rate by a factor of 2, and basically helps us not necessarily increasing the line rate like we were doing traditionally, and actually choke the line a little bit down, and basically that gives us a much better reach. 16 QAM is how we do 200 gig. Now you're seeing 400 gig. This is how we basically attach two 200 gig super channel together, 200 gig sub channels together to make a 400 gig. And basically, this is how you see the signal. Now, each of those have a coordinate, but now that you have 16 symbols, to decide, you're basically doubling your line rate with the same baud rate. I've talked about the SAW effect. What's really cool about the next movie here is you'll be able to see the symbol rate that was captured from a receiver after 300 kilometers, and hopefully the animation will go. And what we did during this exercise is we were carrying traffic, and while we were carrying traffic, we were changing the constellation. Now, hard-fact here is happy. It basically is in the middle of the decision threshold, and there's no problem. But however, if there's some hopefully it's very difficult to see from here, but basically what you're seeing is if it's fuzzy, when it's fuzzy, you basically see the, well, actually that should be better. Basically, when it's fuzzy in the transition, this is where the probability helps you carrying the traffic. How does it look like? Does it look like? It's all right? I let it roll a little bit just to make sure everybody sees it. Now, the cool part about this animation is if you have a very flexible system, you don't necessarily have to have a constellation that is basically standardized. You can try many types of constellation map and get the one that's really working. And sometimes some of the symbol, for those who don't see, there's a smiley face here. You can basically use each type of constellation to do it. And hopefully this is the feature here. You don't see it, but there's Pac-Man. So, okay. Enough of the Pac-Man. Let's talk about a little bit about super channel technology. This is the current way that the DWDM signal is working. You have segregated 50 gigahertz barrier that are displayed here by a gray band, and you have a regular DWDM signal that's basically the red pulse. If you're talking about flexible grid, you're allowing yourself to either remove those barriers that were there or to actually move them away where you see fit. As you can see here, you could never be able to have two super channels superimposed together like this with a non-flexible grid. The idea of the flexibility of the grid is to be able to either move it or reduce the size of the window by a factor. Our technology allows us to do it with a factor of 12.5 gigahertz, and that allows you to have the maximum spectral efficiency that you're looking for when you want to take advantage of the whole C-band, which is the one that we're using when we're doing fiber optic transmission. Let's talk a little bit about SC13 in Denver. So, when we showed up in Denver, we showed up with SciNet, and they had some challenge. We had a very old fiber plant, and we basically were looking to carry a lot of traffic. So what you're seeing here is the SciNet that was supercomputing that was run in Denver last year, and these are the reference of the traffic that was run by respectively Internet 2 and ESNet that were running over the full week of supercomputing. And what's really cool about it is it was working in an existing shelf using existing components. How we built the 400 gig super channel was basically building two 200 gigs sub channels. We were basically co-locating them next to each other, and that was giving us a super channel. The cool thing about this, this slide is you see the difference on a spectrum analyzer of many different channels. This is a regular 100 gig WaveLogic 3. Next to it is a 10 gig signal, which is basically doing amplitude modulation. It is not a coherent transmission transmitter. It is actually a regular transmitter with amplitude mode. The other ones are the WaveLogic 200 gig signals, which you can see the superimposer imposement of both 50 gigabit signal together. And here, you see two regular 200 gig channels separated by a regular positioning in the 50 gigahertz grid, like if they would be separated by a non-flexible grid, like a regular ITU-T grid. The reason where you can take advantage of the flexible grid is you can now push these channels onto one another and basically save some space. We have demonstrated, and by running the system at SC, that we could basically on 100 gigahertz, two channels next to each other takes about 100 gigahertz wide. We were able to squeeze the channels down to 75 gigahertz wide, basically demonstrating that we can really save 20 to 25% of bandwidth just with two channels. If you think about that you have 88 channels or 90 channels, or even 100 channels, just to make the numbers even, if you save 20% of bandwidth, you're actually increasing your bandwidth by a factor of 20%, and that's not necessarily a small change. It's actually quite interesting. This is how it looked like. This was a live system. We were able to capture the constellation which you were seeing in the movie, and that was the optical spectrum analyzer that we were displaying at the show. And basically, the results that we had from the transponder, remember when I was talking about that you can extract some information from a coherent receiver based on its property, we were able to basically run that over a 2.7 kilometer link, but watch the dispersion. Those who know the dispersion numbers, we would be expecting 4, maybe 10 picosecond. We had 82 over a 3 kilometer length. So that was a very, very bad fiber plant. But we managed to get it working. The stability of the system was over 120 hours, which gave us about 6 petabyte. And not a single bit was lost during the process. So even when we were playing with the wavelength, when we were stringing them together. So that was pretty cool. So in summary, we talked about 400 gig that was demonstrated at SC13. We talked about new modulation and super channel implementation that increased the spectral efficiency. We also talked about the importance of spectral shaping and SAW effect to actually optimize system performance and to allow us to get each additional bits further down the fiber link. And we basically have new higher speed technology that would provide increased efficiencies, and basically 400 gig and terabit is actually very real. That's all I have to say today.
Any questions from the audience? Just a moment. Just a moment, please.
You mentioned the dispersion of 82 picoseconds. What was kind of dispersion, CDO, PMD?
It was a chromatic dispersion.
Okay.
It was a chromatic dispersion. The PMD was actually 1 picosecond. So
yeah, but 82 will be definitely something different.
You're correct.
Thank you.
Yes. You have another question there?
Yeah, when you showed the constellations earlier, there are the odd dots that appear in between. What's the relative population of those regions compared to the core of the constellation?
You mean in the transition?
Yeah, the early ones, let's say the 16 QAM one.
This one?
Right, so we see dots in between, which
So
visually could be interpreted as adjacent to either.
Exactly. So if you're using a regular FEC, you're bound to make a mistake and you will lose traffic. By using the probabilities, using a better polynomial, basically active component, you basically will be able to make a better guess, if you will.
So is that log likelihood stuff?
Pardon?
Is that log likelihood estimators?
There are many algorithms. The one that we have is done in real time. But what you're seeing here, what I would like to say here, is this is a MATLAB script that basically takes the symbol directly before they go to the soft decision stage of the ASIC. So therefore, this is the true analog display that the decision block, the soft decision block has to take. So this is what it sees. So that's before it decides if it's a 1 or a 0, or it depends on which, if you will, coordinate it will assign to it. And that is all taken into account the current dispersion of the link and the current dispersion, the current forward error correction that's being taken into account based on how long the system has been running.
Thanks.
No problem. Any other question?
If no more question, thank you very much for your presentation again. And our next presenter will be Ioan Turus, who received his master's from Technical University of Denmark. Currently, he's pursuing an industrial PhD program at NREN in collaboration with Technical University of Denmark. His main interest is software-defined network and open flow, as well as a control plane architecture for elastic optical networks. His talk will be about the evolution of the Flexgrid architecture for NREN's optical networks. Ioan, please give your presentation. Thank you.
So what I'm going to talk is the Flexgrid architecture that I'm implementing and studying in my PhD, and the association I'm trying to do between this and applicability for NREN environments. Yeah. The outline of the talk will be a few words about NREN environment, then an introduction to elastic optical networks, where Flexgrid is coming from, and then a few details on the extensions that need to be performed to GMPLS to support Flexgrid. And afterwards, I will list a number of relevant challenges for Flexgrid and some NREN specific challenges. So the NREN environment has a number of common objectives that is driven the development and their existence, and they would be the support of R&D partners to deliver network services, to enable novel network features in research projects, enable collaborative work in global networking projects. And they have a number of common challenges, which are to deliver network functionality, scalability, and cost all at the same time. And similar to all the other network operators, they are facing a general traffic increase. And they need to be able to implement and test novel technologies. Here we could talk about Flexgrid as well. So when we talk about an optical network of an NREN and taking the case of NorduNet, we can see that compared to an usual network operator, the network is relatively static, so when we have deployed channels, they are usually very well pre-planned and they stay there for a long time. In this case, we have 40G connections deployed and recently new Siena 100G infrastructure. There we used to implement and test time-sensitive application, alien wavelengths experiments. But the observation is that it's very challenging to serve the future behavior of the connections, which seems to expand in the variation of different parameters such as data rate, duration, length, and so on. And then we want to provide a maximum control of the optical spectrum and thereby enable a flexible and scalable network solution. So going back to the introduction of elastic optical networks, not a long time ago, observations start to come about a big increase in the demand, in traffic demand in core optical networks, and this comes from two sources. One of them is the introduction of new access technologies like fiber to the home and high usage of the Wi-Fi and 3G, 4G. And then development of new demanding applications like video on demand, HDTV, and so on. And with this high incoming demand, the way we supply the capacity the way we supply the capacity is not a natural way to face this demand, because we always try to develop new advanced methods and, for instance, modulation formats, but they always go into a saturation because of the limit in distance. So best research in the area is not a long-term solution to cope with the traffic demand increase. And moreover, new and future incoming demands in the core optical network, they switch from a homogeneous behavior to a very heterogeneous behavior. And that means that the capacity of a normal optical connection starts varying between tens of gigabits to tens of gigabits per second. And the distance they are required for goes from very few kilometers to thousands of kilometers. While the lifetime, in terms of lifetime, we don't have any more quasi-permanent connection, but we start having connections with very short duration. And the way to cope with this heterogeneity is to provide a spectral efficiency adaptation. And this can refer to 4 dimensions. One is that for an optical channel, we can vary, as we heard before, the modulation format and the symbol rate, together being able to adapt the data rate. Then we can vary the channel spacing and optimize the usage of the spectrum, and as well tune the forward error correction. And in total, the tunability of all these 4 parameters define the concept of elastic optical networks. In one of the projects we were working on, elastic 100 gigabits per second PDM QPSK elastic transponder was proposed, being able to online tune between all the 4 parameters. And the decision of tuning is done based on variation in the capacity demand, for instance, day-night variation. So during night, when the traffic goes down, we can retune the transponders so they consume much less, providing also energy savings. And also according to the physical property of the layer, signal-to-noise ratio. An example of how these elastic connections can be deployed, having a path requested for 1,000 kilometers, and established for a 400G connection, filled completely in, it is deployed with a QPSK modulation, as an example. Then, if the same optical connection is not completely fed with traffic, but only with 100G, we can decrease the symbol rate, keeping the same modulation format, and then we require much less spectrum. Similar case for a 100G connection with QPSK, but if we take a connection which is shorter in reach of 400 kilometers, similarly 400 gigabits per second. If we increase much more the modulation format, we can at the same time decrease a bit the symbol rate and provide more savings in the spectrum. Similarly goes for a 100 gig connection, and the purpose of all this tuning is that we could theoretically group all the channels in one side of the spectrum and release the other side as free capacity, which before couldn't be used just because it was fragmented in the spectrum. So the Flexgrid came as a transition from fixed grid, where in fixed grid we had channel spacing of 50 gigahertz or 25 gigahertz. ITU-T introduced in 2002 in G694.1, the idea to split the spectrum in very narrow slices of 625 gigahertz. And then these narrow slices, called elementary spectrum slots, could be grouped, and the number of contiguous elementary spectrum slots could form a spectrum slice. So then we are not limited anymore in the amount of spectrum that we want to assign to one connection. And the way IETF recommends to define a spectrum slice is to have a central frequency, which is indexed starting from the central 193.1 terahertz, and the slice width. And here we have 3 examples of slice definition. And for Flexgrid, there are a couple of challenges, apart from just having this very narrow and easily positioned spectrum. We need to provide a capable control plane to control new flexible connection. We need to handle fragmentation. We have a limited minimum channel width, and we need to think about what is the efficiency for different topologies, and what is the pricing when we want to move from a fixed grid deployment to a flexi grid one. as well as particular challenges in NREN environment, and I will emphasize the introduction of photonic services based on Flexgrid. So in our experiments, we implemented a distributed GMPLS control plane to run Flexgrid. The reason for this is because GMPLS is a control and mature solution already present in some operators. It's an out-of-band control plane and allows us to switch the traffic based on labels which can handle time slots, wavelengths, currently spectrum slots, and fibers. GMPLS protocols are based on three main functions. First is the neighbor and link discovery verification. Then it's the signaling, which allows for any requested connection to check the resources along the path and reserve them afterwards. And the routing, which has the role of automatic topology and network resource dissemination. And based on the information gathered with OSPFT, we can perform route computation. For RSVPT, there wasn't much thing to extend for enabling Flexgrid. It was mainly about allowing RSVPT to precisely identify a slice. So we don't identify any more wavelength, but we need to note which is the central frequency of the slice and which is the width. But then in case of OSPFT, things were a little bit more challenging because having so many elementary spectrum slots, all of this had to be advertised all around the network with risks on increasing the total load in the control plane. So for OSPFT extensions, we needed to advertise two types of information. One is quasi-static information. The reason why it's quasi-static is because this doesn't change, but only when there is a network upgrade or network commissioning. And the quasi-static information contains the available central frequencies, the spectrum slot granularity, and the minimum and maximum sizes of the slices, possible for the slices. And then the tricky information is the dynamic one, where OSPFT LSAs need to advertise any change that occurs in the spectrum slot statuses. And this could be done with two different encodings. We got to the conclusion that bitmap encoding offered the best trade-off for these advertisements. Once we propagated all the information about spectrum slot statuses, we could propose some routing strategies. First, referring to shortest path, when we have a request of a slice containing 4 spectrum slots from source to destination, the base case was just to take the minimum number of hops between source and destination. This is a very blind way of doing it. It provides a lot of blocking. But then improvements come by relaxing some of the links, meaning that a policy checks all the links that cannot comply with the requested slice size. And then by disabling those links, we can have a significant improvement in blocking. And more than that, we can define some policies that take into account different parameters in the links. That can be the amount of spectrum the percentage of spectrum that it's occupied, or the amount of fragmentation that is given in one link, and transfer it into a weight which is assigned to a Dijkstra graph, and then the path computed from source to destination is given much more efficiently, lowering the blocking significantly. And the results are that by enabling graph relaxation, we can decrease the blocking with 15%, while adding the link occupancy weights to the graphs, we can decrease the blocking to 70% compared to shortest path. Next issue is fragmentation. Fragmentation can be defined as the impossibility to establish a channel containing contiguous spectrum with width x on a given path, despite the fact that every link on that path has spectrum, a total amount of spectrum bigger than x. So if we imagine at time 1 a channel set up on the first 2 slots, and then at time 2 a channel set up for the slots 3 and 4, but only in the middle link. If we have another channel 3 set up on all the 3 links, it takes the first available slots, which are 5, 6, and 7. But then if at some point channel 2 is released, and we have another request coming for a slice of 3 slots, we obviously cannot serve this new request, despite the fact that we have 4 slots available in every link. Then we are required to provide some way of defragmentation. And the defragmentation procedure that we proposed was a hitless distributed defragmentation based on the GMPLS. And the reason why it's hitless is that all the channels existing in the link, they are not affected. The upper layers, they don't see the change. And distributed is because it's based only on RSVPT propagation and does not rely on OSPFT information. So the way the hitless distributed procedure works is that an RSVPT path message starts going from node A to node E and collects all the previously available slots that could pose a fragmentation. Then the reservation message goes back from D to A and reserves those possible slots. And this now gives time to the laser in node A to retune the channel back to the left without making any disruption. Afterwards, a path message goes from node A to node D and reserves those previously used slots. And now we can have 4 slots available in every link, and that means that channel 4 can now be set up. Another challenge I observed in the simulations was that I was considering many times slices or very small requests of 625 gigahertz, but in practice, when we look at commercial transponders, it's very unlikely to have spectrum slices requested for less than 1875 gigahertz. And an example is for channels established with a symbol rate of 14 or 28 gigabaud. And we can see that for 14 gigabaud, the minimum required spectrum amount is 18.75. And that can be at best served with a grid of 625, the most spectral efficiency with 3 slots, or with 2 slots of 12.5 grid, but that's less spectral efficiency. Moreover, when we have different topologies, it's important to get the efficiency and the gain in capacity provided by Flexgrid. When we see that comparing NorduNet and Giant optical topologies, in both we have interconnected rings. We have in NorduNet topology no edge links, meaning that every node has a degree of at least 2 or 3. And we have relatively few nodes, which is not the case for Giant, which has leaf links and more optoelectronic nodes, meaning that when we establish a shortest path, we have more links on that path, and that will for sure influence the fragmentation. Then, when talking about pricing in Flexgrid, recent studies show that if an operator has a traffic that does not go beyond 37% increase, it's not worthy to upgrade from Flexgrid to Flexgrid in the next 5-year planned investment. And when the investment is done, around 95% of the capex, is given by Mach-sponders and flexible Mach-sponders and regenerators only. And when a plan for this 5-year investment is done, there are different ways for doing it. One, from the point of view of what grid technology we deploy, one is to see what the traffic increase is. And if we estimate that this goes less than 35%, we can think, oh, let's just deploy fixed grid from now. That means that we put in our network only fixed grid nodes and fixed grid Mach-sponder. But this is the cheapest option, of course, but this might bring the risk that what if traffic will raise higher than we expected, and we need to provide more capacity. In the case of fixed grid, we will need to deploy more fibers, maybe, which is expensive, together with more fixed grid equipment, or provide directly Flexgrid after this. While the other way is to provide Flexgrid from day one of the deployment, but this is the most expensive option. Okay, it can cope with any traffic increase, theoretically, but we should see a trade-off strategy between these two, which proposes that in the phase 1, only flexible grid nodes are deployed, but with fixed grid Mach-sponders. And this can cope with the current estimated traffic increase. And when we have surprises in the traffic increase, we can, as requested, provide flexible grid Mach-sponders. The price of such a deployment scenario is slightly higher than in case of deploying fixed grid only, but this comes with the advantage of having a good way to cope with unexpected traffic increase. Then, photonic services, which are more and more a topic of discussion in NRENs, could benefit out of the Flexgrid. I documented a couple of photonic services application, and I tried to map them into requirements for a Flexgrid environment. And the two parameters I considered was the requested spectrum, or how big the slices should be, and the guard band size. So I imagined 4 types of photonic services, depending on the influence on neighboring channels, high or low, and if the slices should be same high or low. So for transfer of broadband frequency, I identified that there is a high request of spectrum, so big chunks of spectrum, and possible big effect on neighboring channels. So this would give relevant input for how to design the part of the spectrum which is going to serve photonic services. And an example is here that we would imagine the left one part of the spectrum working for operational channels, 1040-100G, while the other part working for photonic services. And then we have a dense grid enabled, and we need to see what guard band should we provide between the two sides, as well as what guard bands should we provide between different photonic services. And depending on this, we would have different Flexgrid efficiency. And this is a work that is ongoing now in my studies. So in this example, we have 3 operational channels in the left, a slice of 25 gigahertz for a 100 gigabit channel with QPSK, and 2 slices serving 40 gigabits per second channel with QPSK, slices of 12.5. And then a guard band of 37.5, and imaginary photonic services requiring 50 gigahertz. So this being said, I can conclude that Flexgrid architecture is an enabler of the elastic optical network concept. It poses high complexity on current optical control planes. There are physical limitations still in place, like, for instance, wavelength selective switches. There are challenges that are currently addressed in different research areas, and the Flexgrid architecture is generally becoming mature, so prices are going down. And the Flexgrid migration strategy would be a trade-off between deploying from day one fixed grid or directly Flexgrid, and it's an important technology enabler for both NRENs and RE partners, because it allows to introduce new traffic engineering optimization techniques, as well as possible photonic services in the same commercial fibers. And the ongoing work now focuses on evaluating the possibility of integrating these photonic services in by the help of Flexgrid, and estimate possible accepted traffic growth in an NREN optical infrastructure, in our case NorthernNet, compared to currently present grid of 50 gigahertz or 100 gigahertz. So this was all I wanted to say.
Thank you very much for your presentation. Any question from the audience? So maybe I have one. Yes. You described about the elastic optical network. What about the IP side? How can you benefit? How can you benefit the elasticity in the IP side? Do you see any options or any? What are the possible solution to make it elastic in terms of bandwidth in the IP networks, IP router side? Do you see what can be done on that part?
Yes, well, the main advantage I'm also motivating usually in introductions is that in the IP side we see the variation, the input traffic into this optical core network. And now when we deploy a 100 gig channel, we can see that the incoming IP traffic has some peaks, usually at 10, 20, 30 gigabits per second in our case. And despite this, we have a deployed 100G channel. And this always stays static, consuming the same energy, without being able to adapt at all to the input traffic. So we could say that the incoming IP traffic would drive the configuration of the optical layer with gains in energy efficiency mainly.
And do you think, are there any proposals to do such a controlling of the spectral efficiency and a talk between the router and the optical system vendors?
Yes, there is, and there are in research. This goes pretty well, at least with GMPLS, but it seems very hard to move this dynamicity and the automation from research into production, because very few operators currently run GMPLS to control the core optic.
Okay, question, okay. Thank you.
I have one question regarding the fragmentation issue. You mentioned that you want to reshuffle the channels in the spectrum without hitting the traffic. Did I get you right with that?
Yes,
one?
yes.
I wonder how it works.
Yes, I'm not an expert on physical effects, but as far as I understood, is that if we have this channel tree focused on these three slots in the spectrum, if we have a bigger side of the spectrum reserved and no interference on that part, the laser is able to tune to a bigger side of the spectrum and then retune to the left, something like this. I'm more a control plane guy, but I understood that this laser configuration is working in the lab.
Yeah, just possibly a comment on that one. If you tune slowly enough, and since in a Flexgrid system you don't have dips between whatever channels because these don't exist, if that has been prepared in advance, you simply tune the laser slowly and ideally nothing happens.
Okay, thank you. Thank you for your presentation. And our third speaker will be Klaus Grobe, who received his engineering diploma and doctor degrees in electrical engineering from Leibniz University, Hanover, in Germany. He worked for over 20 years in the fields of lightweight guides and WDM. Currently, he is working for ADVA Optical Networking as a senior principal engineer. He is one of the main authors of the Wavelength Division Multiplexing and Practical Engineering Guide, and authored and co-authored more than 100 technical sub-publications. His research interests include next generation broadband access networks and as well as high-speed DWDM transport. And Klaus will speak about a new kind of infrastructure cloud service called Spectrum as a Service. Klaus, please.
Thank you. Am I heard? I'm not sure. Okay. Yeah, thanks again. Good afternoon, everybody. Thanks for attending this session. You are in a lucky situation because I can save lots of time if I want to, because Marc and Ioan already pointed out my motivation for what we call Spectrum as a Service. I will hence only very quickly go through another motivation of Flexgrid and its capabilities that we internally refer to as SDO, software-defined optics, not to be, of course, not to be confused with SDN. And yeah, let me start and go quickly through it. I think this has really been mentioned. If we start with today's coherent 100 gig system QPSK, as mentioned, with a given baud rate in order to change something, and in the end to change throughput, I have at least 3 directions. I could change the constellation diagrams. By the way, there is also a backward direction going to binary PSK in order to massively increase reach. I can change baud rate, has also been mentioned, and I can do spectral shaping. This has also been mentioned here. I would like to add, theoretically, you could also shape spectrum by going to what is called quaternary partial response, so a complex partial response scheme. Now, part of this has been shown already. For very high bit rates, of course, can be combined with a diversity of subchannels or subcarriers or laser lines that are modulated and then put together to superchannels. And since we do this with, I think starting with 400 gig, maybe 200 if respective interfaces arrived. There is another degree, which is of course the subcarrier spacing and its related shaping. So even if I shape the subcarriers with whatever mathematical functions, I can still squeeze them more or less tightly together. If I put them tighter together, obviously the intra-super-channel overlap increases and hence somewhere bit rates will increase, but I still gain in spectral efficiency, and there's of course a trade-off. If I only need to traverse, say, 200, 300, 400 kilometers, I can do this and still gain in spectral efficiency. This has also been shown. So a typical 400 gigabit superchannel card would then likely have 2 carriers. So if you want to go 400 gig on long haul, you likely have to bond 2 of these cards because you need the QPSK mode. What I will show on the next slide is you have many configurations leading to many reach penalties, but also to very many analog bandwidth requirements. And this, at a certain point in time, maybe not with 400 gig, maybe with 1 terabit per second super channels, maybe if customers want to have more than 1 super channel, lends itself to, well, what we call spectrum virtualization or spectrum as a service. By the way, this in German reads a bit like fun. It's not correctly spelled, but naja, never mind. This little table shows some possible configurations for various bit rates. In particular, here are 2 examples for 400 gig, the 2 usual suspects, QPSK and 16 QAM, with the various penalties that arise from taking more and more subcarriers, also from baud rate, of course. In the end, this translates either to reach or to certain, of course, end to certain bandwidths. And here, we didn't even consider that I still have the degree of freedom of subcarrier spacing. So by no means are these 75 or 150 gigahertz fixed. In particular, they are not fixed if I use partial response for pulse shaping. Then I can do lots of things. And since this isn't fixed anymore, and since I also could take more and more subcarriers toward 1 terabit per second per superchannel transport, and who knows what comes next, well, we need flexible bandwidth. So that was the motivation behind. What we want to propose, and there's some big question marks behind, is a new concept, spectrum as a service. And there are several questions, and we need feedback. And so if there are people interested in please do provide us this feedback. So what it is, what it's about. Well, it is providing spectrum, flexible. That's, by the way, of course, why I am in the Flexgrid session. It really only makes sense if I have a Flexgrid transport system. You could do something similar in fixed grid, but then you end up with all the nasty dips in between the channelized channels. So provide arbitrary chunks of spectrum. Yeah, we will end up in this fragmentation problem. We will end up in many other problems, which I will partially show. But it leads to the provisioning of what we would call virtual private bandwidth. And consider that this spectrum, an arbitrary broad slice of spectrum, would be a service sitting between a wavelength and a dark fiber. So it's really something in between. And one of the many questions is, are there types of infrastructure providers or network providers likely, that could imagine that this is good for their customers? And yes, of course, it requires a transparent transport infrastructure. So it could hence lead to a new type of service, the spectral VPN, if you like. This could mean I can, of course, I have to virtualize my network. I can share this then between several customers using suitable control mechanisms. And again, we even believe this might to a good degree become necessary because of the uncertainty with regard to future, well, both customer demand and also with regard to what future signals may look like. In particular, if you combine this, how does a super channel look like in 10 years from now or 15 years? Is it a 2 terabit or a 10 terabit per second super channel? What if the customer wants to have 2 of them and maybe for whatever reason wants to bond them? So there's a whole bunch of uncertainty. And of course, customers may have completely different requirements. That's why it may be useful to offer them different slices of spectrum only. They may also want to do within their spectrum slice what they want to do and not what the transport network provider wants to do. And as such, a spectrum as a service can of course also be regarded as a generalization of alien wavelength transport. And well, there are basic requirements, at least we identified some of them, leading to at least some hints as how it can be implemented. Oh, I'm on slide 11 already. We need, of course, some signal admission control. This is mainly required for creating the private spectrum. So no other signals must interfere with the private spectrum that I provided to whatever customer. That's clear. We will certainly have some things to do and to consider with regard to blocking of whatever distortions. So it's of course a little bit tricky if the respective network provider provisions part of his spectrum and hence part of his network to his clients, and of course client A mustn't interfere or distort client B, C, D, etc. So we really have to consider both rogue behavior of client signals and of course also well malicious users. And there is then, of course, some physical considerations necessary, in particular crosstalk mitigation. So the network provider or spectrum provider still would need to take care of suppression of transients. What if one of his customers within his spectrum switches on new channels? This would typically lead to whatever transients in the network. Can be mitigated, but needs to be considered. And then, of course, we need to look at least some of the physical parameters of the signals. In particular, it's unlikely, I would say, or at least it would lead to some problems if we allow intensity modulated signals, or we would end up with massive guard bands or some other inefficiencies. Root cause of this is mainly a nasty effect called XPM-induced nonlinear phase noise, cross-phase modulation-induced nonlinear phase noise. That's the distortion caused by intensity-modulated signals onto mostly phase-modulated ones. That's why the interworking between standard 10 gig and 100 gig leads either to some penalties or to some guard bands, etc. And then, of course, we also need some consideration of the respective routing. The customer, of course, shouldn't have, or maybe even can't have, full knowledge of the network. So we need to set up the respective spectrum paths, if you like, based on a limited set of parameters that need to be provisioned through whatever suitable interfaces. One example how it may look like, and also showing one or two, ideally at least one or two characteristics. So the spectral bandwidth per customer, ABC, can or should of course be variable over different links. And in general, it is to be expected that reconfiguration based on suitable control and management mechanisms, well, it should at least be significantly faster, than within a day or so. Maybe within minutes. I wouldn't be too over-optimistic bringing up and maintaining stable, long, multi-hop optical links may require to bring up such spectrum links or spectral VPNs slowly enough just to suppress transients. And this leads to some main functions. So on the network operator side, it's mainly, provision or partition the spectrum within the different links, yes. Ideally, as I already mentioned, this is of course based on Flexgrid. You could theoretically adopt this concept to channelized systems, but keep in mind in a standard or normal channelized system, and if you provision, say, a spectrum of 350 gigahertz or something, you would have 7 dips in between. So you may end up with several problems for at least certain super channel configurations. So it lends itself really to Flexgrid systems. And of course, since we are talking about a version of network or transport topology virtualization, it needs centralized control. You can't virtualize part of a network without a centralized entity. So it may either lend itself to SDN or at least a centralized NMS control, supervision, etc. And on the customer side, ideally the customer uses his spectrum with the services which he defines and not the provider. And that should ideally hold for modulation format, baud rate, the construction of the super channels, etc. With certainly some limitations, but that is to be discussed. I mean, if the customer want to use intensity modulated signals, then within within his spectrum then need to be sufficiently large guard bands. It leads to inefficiency within the customer's spectrum, or a certain penalization, if you like. And again, the provisioning, routing, maintenance, etc. needs to be done via suitable. We say purposely suitable here, because it's by no means defined today. It's not clear yet. By suitable, either UNIs or SDN control, and ideally only by provisioning a limited set of key parameters. For example, of course, the analog bandwidth requirement. That's what the whole thing is about. We certainly will need some basic information about modulation type. For example, as I mentioned a couple of times, intensity versus phase modulation. Even for non-intensity modulated signals, it would likely be good or nice to have some information on the peak to average power ratio, yes. And then, of course, what other physical constraints may the respective customer require. For example, with regard to the OSNR requirements and other constraint requirements that his signals have. And this, in the end, leads, well, likely to a new type of network element, or a new type of, I would say, demarcation unit. It's really a demarcation unit. We call it spectrum gate here. That's just the name. At the time being, it says nothing. On the provider side, we have, as mentioned a couple of times, Flexgrid ROADMs, and in order to maintain network integrity, we need to do certain analysis and diagnosis functions here. But as you can see here, with the gray italic font, most of these are possible or done already today. So it's maybe only some new types of guard band considerations that need to be done, but in a Flexgrid system that's not too difficult. Whereas in the demarcation unit, and the first picture about spectrum as a service showed that the demarcation unit could either be co-located here, if you like, or co-located at the customer premises. That's another degree of freedom that we may discuss. There need to be done some diagnosis functions. We think it is or will become necessary to provide both time domain and spectrum domain or spectral domain signal analysis. And of course, the spectrum gate itself is also the device that provides the physical colorless, gridless ports that also provides or allows the transient control, the required power leveling, and if whatever sits here becomes rogue or even malicious, a forced power shut or port shutdown option. This is, by the way, fully normal to discuss these things in various standardization bodies. If customers go rogue, they go into forced shutdown, full stop. And consequently, a basic starting point or a starting point for a spectrum as a service implementation is for the spectrum gate itself to consist of a combination of VOA arrays that are variable optical attenuator arrays, Flexgrid as well, of course, possible. That is to both manage power levels and also a VOA can perfectly block customers, so it's also to shut down ports, and then means for time domain and frequency domain analysis. And on the other hand, on the provider end, as mentioned a couple of times, Flexgrid ROADMs based on whatever wavelength selected switch technology. And these do the provisioning of the respective spectral bandwidth. They do the routing, the privacy, and also provide, if necessary, the guard bands. And this needs to be obviously supported or complemented by link provisioning first, which can be and would be, for example, in our case, control plane assisted, and the respective aspects of network virtualization toward the customer then is likely to be SDN controlled or supported. That brings me already to my conclusion. In the, well, nearer future, customers may want to get variable bandwidths, possibly as a generalization of the alien wavelengths concept, or maybe because of uncertainty regarding future signal shapes, if you like. This is, as said, alien wave generalization. It requires some basic functions to maintain, mainly to maintain network integrity, like monitoring, signal analysis, suppression of transients, and also shutdown of rogue systems or malicious users. And some of the certainly quite few open questions relate to the respective management or control approach. Could be done both with a centralized NMS and suitable UNIs, or of course could be based on an SDN approach. And then, yes, the set of parameters which would have to be agreed on, which need to be exchanged via either SDN control or the UNI. I gave some examples of some parameters which we see necessary, but maybe other people have other ideas or see more parameters as relevant. And this really, at the time being, is to be discussed, and we are happy for all of these discussions. And that brings me to the end of my talk. Thank you.
Thank you very much, Klaus, for your presentation. Any question from the audience? If not, probably you mostly answered my concern in your presentation. I've seen your previous slides regarding what kind of parameters has to be agreed between the users and the providers. You had some ideas about that one. Are there any serious discussion with some vendors, users about this setup or parameters?
Not yet. It really, hopefully, starts now. This is, in fact, the first time we present the concept. I mean, it's obviously possible with the Flexgrid system and suitable control mechanisms, and the parameters that need to be exchanged, from my viewpoint, but I'm a layer 1 guy, transport guy, really need to relate to physics. Because what we are doing here, unlike in layer 2 or 3, we are dealing with physical links.
Thanks. The most interesting example I've seen of an unconventional optical signal are these band-limited optical frequency comb transfers I mentioned in my presentation this morning, which the national metrology labs are interested in for propagating reference signals essentially between themselves. So that is very different to normal telecoms, and I suspect there might be some research interest in trying to apply these techniques over fibre in that kind of context, not necessarily a production network service. But you can see for that one that anything that would cause shifts, particularly rapid shifts that weren't amenable to servo lock control, would instantly kill such a service. So there's some interesting questions there.
True. I mean, yes. The question is, would that still relate to a whatever guard band discussion? Is it sufficient to provide whatever guard bands, as just one example? And on the other hand, it is likely that not all kind of signals are can necessarily co-propagate on a single fiber system, especially if I open it in that way and provide spectrum instead of channelized, or instead of channels, super channels, let's put it that way. So in effect, my understanding is, unfortunately I didn't attend the talk, but my understanding is it needs or requires very careful mitigation of whatever nonlinear effects. Because I think these are mainly the ones that may distort your signals.
I'd like only to comment on it that some services like precise or not precise frequency transfer needs to propagate into single fiber in both directions, and I think it's that killing fact. It needs to be bidirectional transmission in single fiber.
This was mainly about standard dual fiber. I would have some problems. It could be adopted to a single fiber working, but then likely you would divide the fiber into a spectrum part, so you would at least end up with massive chromatic dispersion issues, etc. So, yeah, to be discussed.
Okay. If no more questions, thanks again for your very useful presentation. And before closing the session, some announcement. After this session, there will be some both and side meetings that you can attend. And for tomorrow, there will be a gala dinner. Don't forget your badges, otherwise you cannot attend. And if you need other ticket, you can buy at the registration. And the last announcement, if you need some assistance to travel on Thursday to the airport, you can ask also at the registration desk. Thank you very much for your attention and attendance of this session. Thank you.